Hello everyone. In this video we're going to be solving a really nice equation with complex numbers. By the way, welcome to aplusbi. This channel is all about complex numbers. In this video we're going to be solving this beautiful equation which is homemade, kind of. Okay, now these equations you can definitely make on your own, but they don't always have nice solutions, which is something that I found out. Anyways, let's go ahead and see how we can solve this problem. By the way, if you're new to complex numbers, go ahead and check out my lecture videos. I also have another channel which I make videos weekly, twice weekly. It's called Cyber Math, and that is cyber with an S. Let me know what you think about those videos. Maybe that's where you came from. Great. Now, we have this equation and how are we going to solve it, right? Now, when you get an equation like this, one of the things you can definitely try is conjugating both sides. Why? Because we have the conjugate of z, which is the complex conjugate, right? And hopefully you know that if z is expressed as a plus bi, z bar can be expressed as a minus bi, which is actually a unique complex number. When you multiply by z and add to z, you always get a real number. That's why it's unique. Okay? Great. Now, so we can try that first, which could be the first method. Doesn't necessarily have to be a successful method because sometimes I just try. I don't even know it works. And it's kind of fun finding on the spot, don't you think? Because I don't edit the videos. Some people do. And some people I know complain that I don't have a script. I don't, okay? I just wing it, okay? Anyways, now let's go ahead and see how we can solve with this method. So I have an equation, and if I can get another equation, wouldn't that be nice? Absolutely. So, and maybe we'll save that for the second method because first method is supposed to be taking longer. Maybe, you know what? Never mind. I'm just going to use it. So here we go. Again, this wasn't planned. If you conjugate both sides, what do you get, right? Let's go ahead and conjugate both sides as a whole. And of course, conjugating right-hand side is fairly easy. It just turns into 11 minus 21i. What happens to the left-hand side is more interesting. You can kind of separately conjugate these, but if you conjugate z conjugate, you get z, obviously, right? It's kind of turning something upside down or flipping the light switch, one and zeros. So, but what about the conjugate of z squared? Now, you got to think about it in terms of multiplication because if you conjugate a product, it's basically the product of conjugates. So, this means that you can take z bar and square it, which is really cool, right? And this gives you z. Nice. And of course, right-hand side is 11 minus 21i. Now I want to go ahead and bring down the original problem and see this makes sense at all. Like my goal is going to be to solve this as a system because I have two unknowns and two equations, so I should be able to solve it, right? Well, kind of. Here's the problem. When you substitute anything for z or z bar, you'll get a quartic equation, which is fairly hard to solve. In some cases, I wouldn't say in some cases, it's always solvable, but equations or solutions may not always be very pleasant. So let's go ahead and do this. Since we want to arrive at z at the end, let's isolate z bar from here. Z bar can be written as 11 plus 21i minus z squared. So this is something hopefully we can use in our first equation, which is this one. By the way, I call this first and I call this second. Okay, so I pull the z bar out from the second equation and substitute into the first one. Great, let's go ahead and do it. We have z bar squared, so it's going to be replaced by 11 plus 21i minus z squared, and then I will have to square that again, plus z equals 11 minus 21i. Remember, we obtained the first equation by conjugating the second equation, which was the original problem, which is funny because normally the original is the first one, but doesn't really matter here. Great. Now, what did we get? A quartic equation. For simplicity's sake, for now, let's go ahead and call this w. It's just another complex number, right? And that's w bar, but that's okay. We can deal with that later. Let's go ahead and expand this. How do you expand w minus z squared squared? That'll be w squared plus z to the fourth minus 2w z squared. Plus z is equal to 11 minus 21i. Obviously, the expression on the right-hand side is a constant as well as w squared. Now we can go ahead and evaluate w squared. Now 11 squared is going to be 121. 21i squared, I forgot to tell you, I always forget this. I squared is negative 1 because I is the square root of negative 1. So 21i quantity squared as a product would be 441 times negative 1, which is minus 441. You see how that works? Great. Now we're going to go ahead and multiply these together. 21 is basically going to be like this. 21 times 11. And then you got to double it, 462. So it's going to be 462i. Remember, I used the formula 2ab for a plus b squared. A squared plus b squared plus 2ab. Okay? Great. That is w squared only, plus z to the fourth, minus 2wz squared. And guess what? I can now replace w with what it is, which is 11 plus 21i, right? Yep. And then plus z, this looks complicated, is equal to 11 minus 21i. All right, great. As I said earlier, this is a quartic equation, and guess what? It has a complex coefficient. But there's no z cubed in the equation. Guess what? We have a z. Too bad. So I was hoping that this would be biquadratic, but that's not the case. This is going to be a full quartic. So it's going to look like this. Z to the fourth minus, and then you're going to have this as the coefficient of z squared, obviously. And then you're going to have a plus z. I think something is going to simplify or cancel out. We're going to have plus z. Really, it's just one z. Okay, fine. And then we have the constants, the coefficients, okay? So let's go ahead and put everything on the right-hand side. So this would be 320, the difference. Of course, that's negative 320. And then when you put it on the right-hand side, it's going to be a positive. So we're going to add it to this number. It's going to become 331. Okay. Now these two are taken care of. Of course, we're also going to be bringing this on the other side. And that'll be a negative. And so these two will be added negatively. That'll be negative 483, negative 483i. Awesome. We got a beautiful quartic equation, don't you think? Yes. Now, here's the issue. There's a quartic formula, but nobody wants to memorize it because it's too big, it doesn't fit anywhere. You can look on Wikipedia for the formula. It's huge. Now, but we can use certain methods to solve quartic equations, which I'll probably just outline here because this is going to take forever. I hope you understand that. So here's one thing you can do. You can find a term that you can add to both sides. And by the way, you can totally just forget about the z and put it on the other side because we're going to be adding something quadratic, right? So whenever you have something like z to the fourth power minus 2kz squared, what do you think you need to add to both sides to make it a perfect square? You can basically just add k squared. So in this case, this happens to be my k actually, which is w, by the way. So you can actually go ahead and replace it with w because we already called it w, right? So if you add w squared to both sides, then you should be getting what you need. But didn't we have a w squared at one point? We probably did. But anyways, this quartic needs to be solved, but that is super duper complicated. I'm going to leave it as an exercise for you, and I'm going to proceed with the second method. Who knows, maybe the second method will also be inconclusive. Okay, let's take a look. So what is the original problem? I forgot. It was z squared plus z bar, which is the conjugate of z, is equal to 11 plus 21i. All right, great. Now let's go ahead and do something smarter, okay? The first method we used definitely turned into something gigantic, and we just couldn't solve it easily, right? Let's go ahead and do this. Since z is a complex number, let's go ahead and replace it with z equals a plus bi, which is significant because it's also the name of this channel, don't you think? Now, if z is a plus bi, z bar is going to be, so we're going to do this. First, we're going to square this and then add z bar, which is a minus bi. Obviously, this equation is going to look much, much nicer, right? Hopefully. When you square this, you're going to get a squared. B squared, I squared is going to be minus b squared for the reasons we mentioned before, plus 2abi plus a minus bi equals 11 plus 21i. Now, let's go ahead and put all the real parts together, shall we? A squared minus b squared plus a, and then the imaginary part is 2ab minus b, nice, times I. And that's equal to 11 plus 21I. Nice. Now this should equal 11 and this should equal 21. See how easy that is? Well, maybe not. Who knows? Now here's what we're going to do. We're going to get a system from here. A squared minus b squared plus a is equal to 11. And then 2ab minus b is equal to 21. Now let's go ahead and factor out a b here. And then write this as b times 2a minus 1 equals 21. Now, at this point, obviously, you can replace b with 21 divided by 2a minus 1 and then substitute it into the top equation, which will give you a cubic, never mind, a quartic, because you'll have 4a squared in the denominator, then you'll make a common denominator, you'll get a to the 4th power. So, probably going to be a lot easier than the first one, because notice that we don't have any complex numbers or complex coefficients. In this case, non-real coefficients I'm talking about. When I say complex, don't get me wrong. So it's probably going to be a lot easier, and you can definitely give it a try. So it's going to look like this. We're going to take this expression, we're going to square that, and then add a to it, and it's going to be 11. Now when you expand it, it's going to look like 441, 21 squared by the way, 4a squared minus 4a plus 1. And then you could probably subtract a from both sides so you don't have to deal with that denominator thingy here. You could even leave the whole fraction by itself and do the cross multiplication. But, you know, this is what I'm talking about. Like, put everything on the left except for the fraction and put the fraction on the right-hand side. And then this will become a little bit more clear so you don't have to deal with making common denominator, which is something that I actually hate. But I don't know how you feel about it. Now, here's what we need to do. We need to multiply these two things, cross multiply, and then that is going to equal a constant. So that's going to give us a quartic equation. And you can definitely try to solve it, distribute and solve it. But I'm thinking at this point, if there are nice solutions, and there are usually, come on, these are competition level problems, maybe Olympiad level problems, and they're usually contrived, which means they use easy numbers, but the solution method is not always obvious, right? Obviously. Now, here's what we're going to do. We're going to go ahead and take a look at this. What if we are looking for really nice solutions? In other words, if you want b to be an integer, 2a minus 1, which is an odd number, by the way, if a is an integer, we want it to divide 21, right? So that we can get an integer out of it. So what odd numbers can divide 21? Think about it. Well, I can think of 1, I can think of 3 and 7. That's it, right? Well, 21 has only 4 factors. Guess what? All the factors are odd, so it could also be 21. What am I talking about? All factors are odd because of the prime factors. Great. Now, what happens for each scenario, right? Let's go ahead and check it out. For example, if 2a minus 1 is equal to 1, right, then we get a equals 1. So a equals 1, this gives us a equals 1, this gives us a equals 2, this gives us a equals 4, and this gives us a equals 11. Let's go ahead and check each one of these values, and if they fail, they fail. Now, if a is equal to 2, and you can kind of plug it in here. Let's go ahead and erase this because we already have the new one. Now, if a is equal to 1, I'm going to get 1 plus 1, which is 2 minus b squared equals 11. This doesn't have any real solutions because b squared cannot be negative 9. Obviously, we're looking for real solutions, so forget about it. This failed. If a is equal to 2, we get 4 plus 2, which is 6. 6 minus b squared is equal to 11. That's not good either. We don't have a solution from here either. That failed. A equals 4 is going to give us 16 plus 4, which is 20. 20 minus b squared equals 11, means b squared is 9, which means b is equal to plus minus 3. This might be a good one, but here's what we need to check. If a is equal to 4, does b actually become 3 or negative 3, right? If a is equal to 4, plug it in. 2 times 4 minus 1, remember that 7. 21 divided by 7 is equal to 3. This is cool. If a is 4, b is 3. Can b be negative 3? In order for b to be negative 3, let's take a look. In order for b to be negative 3, this needs to be negative 7, which means a needs to be negative 3, right? Well, we do know that a can be negative 3, right? So if a is equal to negative 3, then b is equal to negative 3. That looks like a good solution, but we need to check that. okay? Because it needs to satisfy both equations. For example, if -3 does not work, it's 9 minus 9. It doesn't work. So -3 actually fails. I don't know how I got that. I probably made a mistake somewhere. So a equals 4, b equals 3 is a good one. What about a equals 11? Let's check it out. If a is equal to 11, then we're going to get 21 divided by 21, which is 1. b is going to be 1 from here. If a is equal to 11, 121, that's too big. It's not going to work. So too bad this doesn't work either. The only pair that works is a equals 4, b equals 3. A equals 4, b equals 3. This means that z equals 4 plus 3i is a solution. But guess what? This is a quartic equation, so there should be more solutions. How do we find the other ones? Well, that's for you to find out, because this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out Cyber Math and A+BI. And until next time, bye-bye.